Today we're going to talk about modeling using variation. Frequently we use formulas that have already been determined to describe situations. Variation formulas show how one quantity changes in relation to other quantities. There are three different ways quantities can vary. They can vary directly, they can vary inversely, or they can vary jointly. Let's first talk about direct variation. Direct variation describes a relationship between two variables, x and y, that can be written in the form y equals some value k that is non-zero times x. K is the constant of variation. So we read this, y varies directly as x, or y is proportional to x. So for example, when describing underwater swimming, the pressure in your ears depends on the depth at which you are swimming. So the formula, P equals 0.43 D, describes the water pressure P in pounds per square inch at a depth of d feet. So let's think about how the pressure changes as the depth d changes. If d is equal to 20, then P would equal 0.43 times that value d, which would be 8.6 pounds per inches squared. If d is 40, we would just substitute 40 for d, and that would give us 17.2 pounds per inches squared. If d is 80, we would just substitute in 80 for d, and this would give us 34.4 pounds per inches squared. So the depth increases, the water pressure increases, and because of this, the pressure in your ears is said to vary directly as you're under water depth. In the second example, we see that y varies directly as x, and y equals 27 when x equals 6. So we can write the function in general form, and we can substitute in what we know. Y is 27. We don't know the constant of variation k, but we know x is 6. So we can easily solve for k, and we get k to be 4.5. So then to write the function, we just substitute in the k we just found, 4.5, and this would be the function. Now let's talk about how to solve variation problems. First, we write an equation based on the words. Then we substitute in the values in the equation and find k, the constant of variation. Then we rewrite the equation, substituting in the value of k, and then we use that equation to solve the word problem. So in example 3, we see that the number of gallons of water W, when used when taking a shower, varies directly as the time t in minutes. So the first thing I'm going to do is write the general direct variation equation. I'm going to use the variables in the problem, and then I'm going to find the constant of variation. How am I going to do that? Well, I'm going to substitute in this information. When W is 30 and T is 5, I can solve for K and get K to equal 6. Now, what is the function once I substitute in the constant of variation that we just found? W equals 6T. Next, I'm going to solve the problem. How much water is used when we take a shower that lasts 11 minutes? Well, we're going to use 66 gallons. The next type of variation is inverse variation. Again, it's the relationship with two variables, but the general equation is not y equal kx as in direct variation, but y equals k over x, where k is non-zero. And again, k is the constant of variation. And we read this, y varies inversely as k, or y is inversely proportional to x. Now let's look at the next example. When describing how long it takes to go from Houston to Austin, the time it takes to drive depends on the rate at which you are driving. You are given the formula, the inverse variation formula. This describes the time t in hours at a rate r miles per hour. The constant of variation you see is given 165, which describes the distance in miles from Houston to Austin. So again, let's now think about how time changes as the rate, the car's speed, changes. Looking at the equation, we have t equals 165, and here r is given to be 60, which is 2.7 hours. Using the same equation, I now am going to substitute in r to be 75, and this gives me 2.2 hours. If we change r to 85 and substitute into the equation, we see that it takes 1.94 hours. So as a result, the rate, r, increases, the time decreases, and because of this, the time it takes to drive varies inversely as the rate at which you drive. So let's look at an example. Again, it's very important to recognize how it is varying. In this case, it's inversely. So I'm going to write the equation for inverse variation. I'm going to substitute in what I know. So y is 4 when x is 5. So if I want to solve for k, I'm going to multiply both sides by 5, and I'm going to get k to equal 20. I'm going to rewrite my equation with 20 for k, and there's my function. In example 6, the length of a violin string, length, varies inversely as the frequency of its vibration. So let's write the inverse variation equation. Let's substitute in variables that make more sense. The length varies inversely with the frequency of its vibration. Now let's substitute information that we know. A violin string 8 inches long, so length is 8 inches, and the frequency that corresponds is 640. So if I multiply both sides by 640, I can solve for k, and k is going to equal 5,120. So now I can rewrite my equation for this problem. Length equals 5,120, which is k, over my frequency. I can substitute in the length to be 10 inches that is given, and I can solve for the corresponding frequency. So the frequency for a 10-inch string is 512 cycles per second. Now we can also have combined variation, meaning we can combine direct and inverse variation at the same time. For example, as the advertising budget A of a company increases, the monthly sales S also increase. So this would represent direct variation. So the sales vary directly as for advertising budget. Sales vary directly with the advertising budget. By contrast, as the price of the company product P increases, its monthly sales S decrease. So we can see that this is inverse variation. So the monthly sales vary inversely as the price of the product. The sales vary inversely with the price of the product. Now we can combine these two variation equations into one. The sales vary directly with the advertising budget and inversely with the price. So this describes that the monthly sales S vary directly as the advertising budget A and inversely as the price of the product P. Now in the next example, we have the number of minutes, which I'm going to refer to as the variable M. So the number of minutes needed to solve the problems on a My Math Lab assignment varies directly as the number of problems and inversely as the number of people working to solve each problem. So how can I write that equation? So let's go ahead and write the equation to represent this problem. The number of minutes needed to solve problems is directly proportional to the number of problems, which we will call P, and inversely proportional to the number of people working to solve each problem, which we will call N. Now, let's go ahead and substitute in what we know. It takes 4 people 32 minutes to solve 16 problems. So 32 minutes is how long it takes 4 people to solve 16 problems. So we can solve for K. If you multiply both sides by 4, we have 128 equals 16K. Continuing to solve for K, I divide both sides by 16. So I get my constant of variation to be 8. I'm now going to substitute that back into the equation that I began with, my combined variation, and now I can answer how many minutes M will it take 8 people to solve 24 problems. And I'm going to get that it takes 24 minutes. Finally, we can talk about joint variation. Joint variation describes a relationship among 3 variables. We've only been working with 2 variables, and now we can introduce a third variable. It can be written in the following form. Y equals K times X times Z. Again, K must be non-zero, and it is still the constant of variation. And we read this as Y varies jointly as X and Z. So in example 8, we have the volume of a cone, V, varies jointly as the area of the base, B, and the height, H. The volume of a cone is 12 pi feet cubed. So I'm going to substitute 12 pi in for my volume. Then I have a base that is 9 pi feet squared, and the height that is 4 feet. So now I can find the constant of variation. I have 12 pi equals K times 36 pi. If I divide both sides by 36 pi, I can get my constant of variation to be 1/3. Now I'm going to substitute back that into the equation, substituting in for the constant of variation K we just found, and I can answer the problem. Find the area, so we're finding B, when the volume is 24 pi and the height is 9. So I can simplify the right-hand side of the equation. 3 goes into 3 once, 3 goes into 9 3 times. So I have 24 pi equals 3b. Now if I divide both sides by 3, I'm going to get b equals 8 pi feet squared.